So, have you ever really thought about the word spin? I mean, it's everywhere, right?
Yeah, it really is.
A basketball spinning toward the hoop, a dancer doing a pirouette, even the earth under our feet.
Right.
But have you ever stopped to think about what spin actually means?
It's funny how we use these words and we never really, think about it.
Exactly. And today we are going deep, deep down into the surprisingly complex world of spin in physics and math.
Yeah,
And trust me, it's way more interesting than it sounds.
it is.
Our guide for this deep dive is a fascinating research paper by Robert A. Close called The Different Meanings of Spin.
Okay.
Now, get this. Close says there are actually 3 distinct types of spin,
Wow.
each with its own, quirks and implications. So we're going to unpack all 3, starting with the one we're most familiar with, kinetic spin.
Okay, so when we talk about kinetic spin, are we talking about rotations per minute?
That's exactly it. It's the everyday spin, like how fast something is actually rotating, revolutions per minute, like you said,
Yep.
a planet on its axis, a figure skater pulling off a dizzying spin. It's all kinetic spin.
Gotcha. So if we can measure it in rotations per minute, we're talking about kinetic spin.
Pretty much. Though Close also mentions this thing called vorticity, which is kind of a way to describe more complex rotational movements, especially in liquids.
So, give me an example.
Think of a whirlpool.
Okay.
The water isn't just spinning in a circle,
Yeah.
right? It's also being pulled inward.
Right.
Vorticity captures that 3-dimensional aspect of the spin, how the rotation changes as you move closer or further from the center.
Okay, so it's not just about the speed, but also the pattern of the rotation.
You got it. And that's just kinetic spin. Close says things get even wilder when we start talking about geometric spin.
Oh, okay, so we're moving on from the spinning tops to something a little more out there.
Definitely more out there. This is where we leave the realm of everyday experience and start to see how spin helps us understand the very shapes and symmetries that kind of govern the universe.
Okay, now you've got to tell me more about this geometric spin.
So imagine a square.
Okay.
If you rotate it 90 degrees, it still looks the same, right?
Right.
That means it has rotational symmetry.
And a circle would have infinite rotational symmetry.
Exactly. Because it looks the same no matter how much you spin it. But here's where it gets kind of mind-blowing. This concept of rotational symmetry is directly tied to spin as a quantum number in the world of tiny particles.
Wait, are we talking about the tiny particles that make up everything around us?
The very same.
Wow.
In quantum mechanics, they assign a spin number to particles based on their, their rotational symmetry.
Okay.
So that square we talked about. In the quantum world, they'd say it has a spin of 4 because it gets back to its original orientation after a quarter turn.
So different shapes have different spin numbers because of their the way that they are symmetrical.
Exactly.
Okay.
Pretty neat, huh?
Yeah.
But Close called this stuff mind-blowing, and we haven't even gotten to the really weird part yet, right? He mentioned something about spin-a-half system.
Spin-a-half. Okay, I got to be honest. I'm a little lost here. What is a spin-a-half system?
Okay, so you know how, in our everyday world, things need a full 360-degree rotation to look the same again?
Right, like a full circle.
Right. Well, a spin-and-a-half system needs to be rotated twice, a full 720 degrees, to get back to its original state.
Wait. You're saying there are things that need to spin twice to look the same?
Yeah.
How is that even possible?
It's one of those quantum mechanics things that it's kind of hard to wrap your head around.
Yeah.
Think of a spinning top.
Okay.
You turn it 360 degrees, it's back to its starting point.
Right.
A spin-a-half system is like this weird, mirrored top or something. You'd have to spin it all the way around twice for it to look the same.
Okay, I'm trying to picture this.
It's tricky. You won't find anything in our everyday world that acts like that. But in the quantum realm, particles, like electrons, actually behave this way.
So electrons, the things that power our phones and computers, they have this double spin thing going on.
They do. And it's not just some mathematical quirk either. This spin-a-half property of electrons is super important to understanding, how they behave.
Right.
Which in turn underpins a lot of modern technology.
Interesting.
So that's geometric spin. It connects the shape of things to the behavior of, these tiny particles.
It's pretty amazing stuff.
It is. And it lays the groundwork for understanding the most mind-bending type of spin, dynamic spin. This is where spin starts to touch on, the very fabric of reality itself.
Okay, now I am really intrigued. Tell me more about this dynamic spin.
Dynamic spin. It
Yeah.
sounds kind of intense.
It does.
Like we've graduated from spinning tops to like the secrets of the universe here.
Yeah.
So where do we even begin with this?
Well, at its heart, dynamic spin is all about angular momentum. That spin energy we were talking about earlier.
Right.
But instead of describing the rotation of a whole object, it represents the intrinsic angular momentum of the medium itself.
Okay, so instead of an object spinning in space, it's more like we're talking about how space itself might be spinning, or like carrying angular momentum.
You're getting close. And this is where things get really interesting.
Okay.
Because, you see, there's another type of angular momentum called orbital angular momentum,
Okay.
which is all about movement around a point.
Okay.
So think about the Earth orbiting the sun.
Right.
That's orbital angular momentum.
So like a planet going around a star, that's orbital, but then the planet spinning on its axis, that would be its dynamic spin.
Exactly.
Okay.
Two different types of angular momentum, describing two different types of motion. But here's where close blows our minds.
Okay.
What if we think of those tiny particles like electrons,
All right.
not just as, little balls of stuff,
Yeah.
but also as waves propagating through space?
Oh, here we go. The wave-particle duality.
Yeah.
It's always kind of tripped me out, to be honest.
Yeah, it's definitely one of the weirder concepts to try and wrap your head around.
For sure.
But if we embrace this idea that particles can act like waves,
Okay.
then their dynamic spin, that intrinsic angular momentum,
Right.
it takes on a whole new meaning.
Okay.
It suggests that this spin energy might be fundamentally tied to the way these waves move and interact.
So it's like instead of a planet spinning in space, we're imagining like a tiny little wave with its own spin zipping through the universe.
Precisely. And to describe this behavior mathematically,
Okay.
physicists use something called the Dirac equation.
The Dirac equation.
Now, I won't bore you with all the details,
Okay.
but the Dirac equation is a fundamental equation in quantum mechanics
Okay.
that specifically describes the behavior of those spin-and-a-half particles that we were discussing earlier.
The ones that need a double rotation to look the same.
The very same.
Wow.
And what's amazing is that the Dirac equation seems to hint at a deep connection
Okay.
between the behavior of waves, like in elastic solids.
Okay.
Imagine a vibrating guitar string
Right.
and the quantum world of particles.
Hold on. Are you saying that, like, understanding how a guitar string vibrates could help us unlock secrets about, like, the quantum world?
That's what Close seems to be suggesting.
That's wild.
It's a mind-boggling idea
It really is.
that these two seemingly unrelated areas of physics could be linked
Right.
through this concept of dynamic spin.
Wow.
So we've got this idea of dynamic spin as, the intrinsic angular momentum of a medium,
Okay.
possibly even space itself.
Right.
And we've got the Dirac equation, which describes how these spin-and-a-half particles behave
Okay.
and might even connect to things like vibrating strings.
Right.
But Close introduces one final piece to the puzzle here.
Okay, there's more.
There's more.
Hit me with it.
Something called spin density.
Spin density.
Spin density.
Is that, like, how much of that spin energy is packed into a certain area?
That's a great way to think about it.
Okay.
Spin density essentially gives us a way to measure how much of that intrinsic angular momentum, that spin energy, is present
Okay.
at each point in a medium.
Okay.
Think of it like this.
Okay.
Imagine a spinning top.
Okay, yeah.
If we zoom in close enough, we might find that different parts of the top are actually spinning at slightly different speeds.
Yeah, I can see that. Like, the very center of the top might be spinning faster than the edges.
Exactly.
Okay.
Spin density lets us map out those differences in spin energy within the top,
Gotcha.
or even within something like a wave.
Okay.
And here's where it gets really interesting.
Okay.
In classical physics,
Yeah.
we usually define angular momentum relative to a specific point,
Okay.
like the axis of rotation. But Close explains that spin density allows us to define angular momentum in a way that's independent of any specific coordinate system.
So we're essentially like removing the need for a fixed point of reference.
Exactly.
Wow, okay.
And that has profound implications.
Okay.
It suggests that this spin energy might be a fundamental property of the medium itself,
Okay.
not just a consequence of how things are rotating within that medium.
Wow. Okay. I need a minute to, like, process all of this.
That's a lot.
We've gone from like spinning tops to the very fabric of reality in like the span of like 20 minutes.
Right.
My head is officially spinning.
As it should be.
So we've got kinetic spin, we've got geometric spin, we've got dynamic spin.
We got a lot of spin.
We have a lot of spin.
Maybe we should,
Maybe we should take a breather.
Yeah, take a breather and come back.
And then we'll try to like summarize everything.
Yeah, and bring it all together.
Sounds good.
Sounds good.
Okay, so spin. We've got kinetic spin, geometric spin, and dynamic spin. It's a lot.
It really is a lot to take in. I mean, Close's paper does a great job, though, of showing us just how connected these different types of spin are.
They really are. So let's try to like bring it all back around, summarize. Kinetic spin.
That's the easy one, right?
That's the one we all know how fast something is rotating. Planets spinning, dancers twirling.
Right. Easy peasy.
Then we went like full on quantum with geometric spin.
Quantum.
Where we learned that particles have this property that's all about how they change or don't when they're rotated.
And of course those spin half systems.
Oh yeah.
The ones that need that double rotation.
It's still blown my mind a little, I gotta say. That's even possible.
It's wild.
But then dynamic spin, that's where things get really kind of out there. This idea that spin energy could be a fundamental property of the medium itself, or even, space itself.
Right. And that's where it starts to get really exciting. Because if that's true, if dynamic spin really is this fundamental property of the universe, then understanding it could unlock some of the deepest secrets of how the universe actually works.
Especially with that connection to the Dirac equation. Who knew a mathematical equation for, describing tiny particles could be linked to the way a guitar string vibrates?
It's incredible, right? It just shows you that the universe is full of surprises, and sometimes even the things that seem totally unrelated, totally different, can actually shed light on each other.
It's all connected. So to everyone listening, next time you see something spinning, maybe take a minute to really think about it.
Yeah.
From the earth under our feet to those electrons, spinning around in our atoms, spin is everywhere.
It connects us to, the most basic laws of physics.
It really does. Robert A. Close, The Different Meanings of Spin, everyone. Check it out. It'll get your head spinning.
It will, for sure.
Until next time.